Okay, this is a video about infinite series, kind of an intro to them, and this is part one. There'll be a part two also a little bit later. So let's say you had a sequence xn. So what we're going to do is define a new sequence that we'll call Sn, and here's how we'll define it. So the first term in S, the sequence Sn, will be just the first term x1. So S1 is just x1. And now for S2, the second term in my new sequence, what I'm going to do is add the first two terms of my sequence I started with, so x1 plus x2. And what I want you to notice is that, well, x1, that's the same thing as s1. So how do you get s2? You just take s1 plus the next term. S3, what are we going to do? Well, this 3, how you should read this, maybe you see what we're doing, we're going to add the first three terms of my sequence xn. And what do I want you to notice? That's the same thing as, well, that's S2 just plus the next term in my sequence. So I could think about that as S2 plus x3. So I think you see the pattern. In general, Sn will be the sum of the first n terms of my sequence xn. And what I want you to notice is that this much here would be S sub n minus 1 just plus xn at the end. And that's what I have here. So what we're going to do is we're going to name this thing. We're going to call Sn, the sequence Sn, we're going to call that the series generated by the sequence xn. And in particular, each individual Sn is going to be the partial sum of the series. We'll call it the nth partial sum of this series here. So there's some notation. So a series in particular is just a special type of sequence. And we'll typically denote both the series and the limit of the sequence. So in other words, the sequence of partial sums, in other words, the series, and the limit of the sequence of partial sums, these are all the same thing. We're going to denote them by the same notation. We're just going to call them with the sigma notation, adding up all the terms xn, or sometimes we'll be lazy, and it's just implied that you have an infinite sum here, and it's just a series xn. By the way, too, maybe it makes sense for our sequences that we start at 1, but as you know, you've probably run into series before this in your life. You could start anywhere in a series, really, so don't be too attached to n having to be 1 down there. And I will probably use this notation more often if you do like maybe a proof of some results, say. Okay, and so by the way, if this limit, the limit of the sequence of partial sums exists, if the limit of the series exists, we're going to say that the series xn converges, and otherwise we'll just say that the series diverges. So let's look at an example that you probably encountered in a Calc 2 class. So if you've got a real number, let's say that we define a sequence that is just based on taking powers of that real number, and I'm going to tell you here that I start taking powers when n equals 0. So I'm going to take, my sequence would be r to the 0, the next term would be r to the first, the next term would be r squared, etc. And so what this sequence generates then, what if I add all such things up? That would be the geometric series summation r to the n, and again, if I just added up all the terms in this sequence, then I get the series that I've highlighted below. And what we're going to do is we're going to see that when the absolute value of r is less than 1, so if r is a number like -1/2 or 2/3, then this series, if I add all this stuff up, it converges, and I can actually tell you what it converges to. All that stuff would add up to 1 over 1 minus r. So how would you show such a thing? First of all, why is this important? Well, because we know something about the powers of r to the n. I know that when r is a number like -1/2, when I take higher and higher powers of that, you're getting a smaller and smaller number. So I know that the limit of r over n is equal to 0. So that's why this is important for me. So let's bring in the series. So what we need to do, remember, a series is always kind of determined by its sequence of partial sums. So maybe it's a good idea to write out what do the partial sums look like for the geometric series. So Sn would just be the sum, again, of the first, in this case, n plus 1 terms, since I start at 0, for n greater than or equal to 0. Okay, so what we're going to do is we're going to multiply both sides of this equation by r. And so what would that do? Well, I'd get r times Sn on the left, and then this guy would become an r, but then everybody else's power here just jumps up by 1. I hope that you see. And now what we're going to do is we're going to subtract. We are going to do this equation minus this equation. So that's this here, that's the left side, Sn minus r Sn. And then if I was to do this minus this, that's what I'm trying to tell you is right here. And what we'll do is we'll try to notice, hey, there's lots of good stuff that cancels over on this side. So in particular, here's plus r, here's minus r, here's plus r squared, here's minus r squared. In fact, all of this is going to cancel out. So everybody here cancels out, well really I guess except for the 1, sorry. So all these r's cancel out, and what do you have left? All that stuff cancels out. You should just have that 1 in front minus this r to the n plus first power. That's my next line. And then now what I'll do is I'll get Sn by itself. So I've factored out Sn, and now I'll divide by 1 minus r in the next step. And then now what I'm going to do is I'm going to take the limit of both sides. So remember, the limit of Sn is what this series should be. It should be what the infinite sum is there. And so if I take the limit of both sides, I'm going to apply my limit laws as well, where it's the limit as n goes to infinity, right? And so, well, I mean, here's the only thing that's got an n on it. What do I know from above? Oh, when the absolute value of r is less than 1, that guarantees me that r to a power, to an increasing power, goes to 0. So in particular, I can conclude that this goes to 0. And what do you get then? You just get this is equal to 1 over 1 minus r. So that would be a way to actually prove, again, that this adds up to this whenever you've got an r whose absolute value is less than 1. So that is our first experience with series. So what else can we do for now in this video? What we'll look at next is what's called the nth term for divergence. The nth term test, for divergence. So what does it say? It tells me that if a series xn converges, then the sequence that generated the series has to go to 0. So how would you prove that, first of all? So, well, if this happens, so we should suppose that the series xn converges. And what does that mean then? Well, that means that the sequence of this thing's partial sums converges, and I'll denote those by sk, say. And so, in particular, if this converges, let's give it a name. Let's say that the limit of the SNs is L, where L is some real number. Then what can you say? Well, what does xn look like? I hope you agree and think about it maybe. This particular term in your sequence should be the difference of these two partial sums. So what does that tell me then? Well, why don't I take the limit of both sides of this? Well, if the limit of this is L, that's what this says, well, this ultimately should go to L2, right? You're just starting maybe one term less. And so the point is, this is L minus L. And I'm pretty sure that that's 0. So what did we just show? We showed the limit of the xn's is equal to 0, which is exactly what I wanted to prove up here. The limit of the xn's is 0. So the contrapositive of the nth term test is a quick way to identify if you've got a divergent series on your hands. So what would the contrapositive of this be? Well, it would be if the limit of the sequence that generated the series, if the limit of the xn's is not 0, then you could conclude that the series is divergent. And so how would we use this then? Let's say that I have this series here, minus 1 to the nth power, and I'm adding all these up. So this would look like minus 1, plus 1, plus minus 1, plus 1, etc., right? What does that up to? And what we're going to look at is, I guess I got to undo those. Here, this is, I didn't want to do that. There. This is your sequence, right? That's xn. And what do you notice? Well, wait a minute. The limit of xn is not 0. So therefore, what can we conclude then? Well, then your series diverges. And again, what do we just have? The limit of the xn's is not 0. So we've got, when this does not happen, contrapositive, right? Then this does not happen. And that's what we're concluding down here. So notice there's very little math at all. It was just using that theorem. So maybe no hard work is what I meant. So similarly, something like this, n plus 2 divided by 100n minus 7. Well, in this case, this is my sequence that generates the series, n over n plus 2 divided by 100n minus 7. And what happens when you take the limit of this sequence? Well, you would get 1 over 100 when you take that limit. And so, well, 1 over 100, yeah, it's pretty small, but it's not 0. So, again, when the limit of your terms is not 0, then you can conclude that your series diverges. Cool. And maybe a way to think about this, right? What this is trying to say is that eventually this is like adding 1 over 100 to itself infinitely many times, which does not ever level off anywhere, right? So in other words, that thing should diverge. All right, so be careful that you read the nth term test for divergence correctly. This is like the biggest mistake that kiddos do in Calc 2 when they get to sequences and series. So to say that the limit of the xn's is 0, that's not a check that says that your series converges. So like this is not going to imply that your series converges necessarily. So to give you an example here, let's look at this series 1 over n. And so here, what are you adding up? What's the sequence? It's 1 over n. And we'll notice like, hey, 1 over n goes to 0. And so what my complaint is, there are tons of Calc 2 students would tell me, therefore, since limit of 1 over n equals 0, that means this converges. wait a minute. This was called a test for divergence, right? I didn't tell you anything about a test for convergence, so whoever did that really read this wrong. So what we need to be careful about here is the fact that the terms go to 0, that does not guarantee that when you add them all up, it should give you something that's finite. So does that mean that 1 over n converges? The answer is no. And so let me show you why. And so this is kind of a neat little proof. By way of contradiction, let's suppose that this stuff did add up to some number s, so some real number s. Well, let's write out what s is. So what would that look like? Well, I'm going to add all these terms to themselves. So it would be 1 plus a half plus a third, blah, blah, blah. And I'm just going to group them in this slick kind of way. 1 plus a half plus 1/3 plus a fourth. And I'm just grouping them again. And you'll see why the parentheses are important in a second. Because, well, this would be bigger than, I mean, if this is 1 plus a half, I'll change this 1 to a half. Well, that'll be bigger. And similarly, I'll change this 1/3 to a fourth. So I hope that you agree that this inequality is true. And then similarly here, I'll make this smaller by making that a half is 2. But now what do you notice? That's 1 plus a half, blah, 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 plus 1 over n. And really, I guess technically there should be plus dot, 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 plus dot, 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 there. But what do you get in the next line? This should be equal to then 1 plus a half plus 1 over n plus dot, dot, dot. Well, who is this again? Isn't that the same thing as my series? Yeah, you're right. And what do we suppose? We suppose that that adds up to s. Okay, what do you have then? I have that s is larger than s. And that's ridiculous. That's a contradiction. So therefore, we just showed that it's not possible that this adds up to anything. So this series diverges. So be careful with that. So last thing I want to talk about is the Cauchy Criterion for series. So remember the Cauchy Criterion, rather than dealing with like what a limit actually is, right? What if I just described to you the behavior of, the terms when you get really far down in your sequence? So the Cauchy Criterion says, for a given series converges if and only if, for every epsilon bigger than 0, there exists some natural number such that once you have two indices, m larger than or equal to little m, which is larger than or equal to this magical capital N here, the partial sums should be arbitrarily close to each other, is what this says here. So the partial sums should be within epsilon of each other. So let me give you an example about like how would you use the Cauchy Criterion to do something. And so this would be useful to prove something like if you have two convergent series, then like their difference is convergent, say. So let me give you some idea, some scratch work maybe. What would be the partial sums for this series here? Well, I'll call it Sn. And what would you do? You would take the difference of the first two terms plus the difference of the next two terms, etc. What we're going to do is start playing with that. And the goal is to maybe pull this apart to try to relate these partial sums to xn and yn. Series xn and series yn. So if I assume that little m is larger than or equal to capital N, what if I look at the difference in these two partial sums? And I wrote them out and I tried to color code them so that you see them. But if you notice, if m is larger than or equal to capital N, then I claim that these blue expressions here, they're somewhere lost in, well really, they're all here, right? So maybe just to convince you of that, right? What am I trying to say? Here's x1 minus y1, and it's minus that, right? And then here it is here, so those should cancel, right? So what I'm trying to say is that all of these should eventually cancel in the dots here. And what would you have left? Well, if you canceled up to the nth term, the next one you should start with is the n plus first term. Up to, you get to the nth term. And I think that's my next line. And so again, when you do all the cancellations there, this would be the first one that you start with, the n plus first term of that, and then up to the last xm minus ym. And then now what we're going to do is, well, I can rearrange these things and get the x's together and get the y's together. And then what I hope that you notice is that, well, this is the difference of partial sums for the series with x's, and this is the difference, this is the difference of partial sums for the series with the y's. We can split this up with the triangle inequality, and I know that because xn and yn converge, at this point, I could go far enough out in those partial sums to ensure that each of these pieces are less than epsilon over 2. Because again, those series converge, and thus when you add them together, it should be less than epsilon. So what I'm going to try to do is give you the formal version of that right there. So why don't we let un be the partial sums of the x's, and let's let vn be the partial sums of the y's. So what do we know? Well, by assumption, the sequence of partial sums, in other words, the series, this is the series xn and this is the series yn, those both converge. And so what does that mean then? Well, that means that there exists some capital N such that eventually the difference in the partial sums for the x's should get arbitrarily close, and the difference in the partial sums for the y's should get arbitrarily close. And in particular, I want to make them both within epsilon over 2 of each other. So now what I'm going to do is I'm going to define Sn. It should just be the difference in the partial sums of the x's and the partial sums of the y's. So if I was to do this minus this, I hope what you see is that's the same thing as if I regroup them, x1 minus y1 plus xn minus yn. And then what I've kind of done is just reformulated what I have for you up here. So I'm not trying to tell you anything different. It's just a little bit more convenient for me to do it this way. So for all indices larger than or equal to that capital N then, what do you get? The difference in these partial sums, again, the partial sums for the difference of xn and yn, that would be equal to, well, um minus vm minus un minus vn. What we'll do is we'll rearrange those parentheses inside. Let's get the u's together. Let's get the v's together. Let's use the triangle inequality. And again, by hypothesis, I know that I could go far enough out of my series here so that each of these is less than epsilon over 2. Therefore, the difference in partial sums of the difference of the sequences is less than epsilon.